Okay, number one. The reason I put this problem on here is a lot of students really confuse independent with mutually exclusive. So I thought these two questions can help solidify that. So this first question is asking if two independent events with non-zero probability, if they're independent, then it's saying there has to be an overlap. So one way to maybe look at this is see if is it possible to have a situation where there's no overlap and see if it can be independent. And that also helped this other question, question B. So remember what mutually exclusive means. That means that they both cannot happen at the same time. Being in one set excludes the possibility of being in the other. So let's start that off with a Venn diagram here. I'm going to make a set A and a set B. And you can see that they're mutually exclusive because there's no overlap. And just to put some concreteness around this, I'm going to create this as an example. Think about you're standing on a wall, and I've got two targets on the wall, target A and target B. And then this square here is the wall. And what I'm writing here is probabilities. You're going to stand away from the wall and throw a dart at it. And what this represents is the probability that if your dart's going to hit target A is 25%. Probability your dart hits target B is 25%, and the probability that you hit the wall and miss the target is 0.5%. These all add up to 100% or 1, so we're good to go. So now the question is, are A and B independent? Well, let's think again. Think about what they are. A is I hit A, and then the event B is that I hit B. Again, for them to be independent, that means that the occurrence of one of them can't influence my probability of the other one. It's just like the goat example. Like when we opened the door, that changed my view of the probability. Or the quiz example, when I revealed the gender of the person who failed the quiz, that changed everybody's probability. So those events were in fact dependent. So let's think about this. If without any information known, the probability of hitting A is going to be 0.25. If they're going to be independent, what has to be true is that the probability of A has to equal the probability of A given B. If that's true, that means B occurring did not change my view of the probability. So let's think about this guy right here. What is the probability of A given B? Well, given B means I have to limit myself to the B event first. That's what it means to be given B means I know that B happened. So I'm going to go ahead and shade B in. So that means I have to limit myself to this region in order to figure out the probability of A given B. So that's what I've done here. That's the given B part. And now I have to say, what's the probability that I'm in A given that I know I have to be in this red area? Well, in this case, that's going to be 0, right? If I'm in B, there's no possible way I could have been in A. You know, if you threw the dart and I told you were in B and then asked you what the probability you hit A was, you'd answer 0. Well, that does not equal 0.25. So this situation is dependent. And so we've just shown that any mutually exclusive situation, they're going to be dependent. So two independent events has to have an overlap. Let's think about B. Really, we've done B here too, that mutually exclusive events A and B are always dependent. We've just really shown that up here. By showing them mutually exclusive, we've gone through and shown that being in one means you can't be in the other. So that means they have to be dependent. Knowing that I'm in one tells me some information that I'm not in the other. So this is also going to be true. Okay, problem 2. We have a pair of dice. Find the probability that the sum on the two dice is 11, given that the sum is higher. I think it's helpful in these kind of problems to just really write it out with the probability notation. So let's just think about what it is we're looking for. We want the probability that the sum is 211. Sum on the two dice is 11, so we want the probability that sum equals 11. That should be an equal sign there. Given that we know the sum is greater than or equal to 7. Well, first to do this, we need to write out the probability grid for throwing two dice and add the sum. Okay, so here I have my grid for die 1 and die 2, and I'm just going to fill this in with the sums. So 1 plus 1 is 2, 1 plus 2 is 3. So in the pattern here, you can convince yourself, is it's just that this sum is the same along all these diagonals. So I'm going to go ahead and just fill that in quickly. We got 7, 7, 7, 7, 8, 8, 8, 9, 9, 9, 9, 10, 10, 11, 11, and 12. These dice problems, I always encourage you to think about it with this square matrix approach and write all the choices in. It just helps you not forget anything. So now here is our sample space. We have 36 possible outcomes. And again, this conditional probability, all we want to ask ourselves is, given, what is the probability that the sum is 11 given that the sum is greater than 7? So the first thing, when we have this given greater than 7, we need to limit ourselves to that. So I'm going to go ahead and outline that region in green here. If I'm given that the sum is greater than or equal to 7, I know I'm inside this green region. And we can count those up, and we could say that the number of elements in the green region equals 21. So now I know, now that I've limited myself, that's what this conditional probability means. Well, let's find the ones that are in fact 11. Well, again, I have to stay inside this region here, and then we can see I'm circling the 2 that are 11s. And so now we have all the information we need to do the problem. Again, probability is just a simple ratio typically. Probability in this case is going to be the 21 elements that are inside the green, because that's where I am conditioned on. And then the numerator is going to be those top 2 11s right there. Pretty straightforward problem. So here for number 3, I've gone ahead and pre-drawn a tree diagram. And B and F stand for selecting the bias coin and the fair coin. And then after I've selected those, I can go ahead and flip. So let's write the probabilities. Remember, there's 2 coins in my pocket. One's fair, one is biased, and it's double-headed. So there's a 0.5 chance that I could have picked the bias coin. There's a 0.5 chance that I could have picked the fair coin. And then once I flip the bias coin, well, there's going to be a 100% chance of throwing a head and a 0% chance of throwing a tail because it's loaded. And then this one here, there's a 0.5 and a 0.5. Again, with any probability tree diagram, now I want to know what's the probability that I've traveled down all these paths. What's the probability that I picked the bias coin and then flipped the head? Well, I multiply these down the branches. 0.5 times 1.0, that probability is just going to be 0.5. The probability that I picked the bias coin and then flipped tails, well, that has to be 0, multiplying them down. Tails were impossible, so it should feel reasonable that that's 0. And then down this path, that's a 0.5. 0.5 times 0.5, that's 0.25. And then here is 0.25. So now that I've outlined all the possible outcomes, what is it that I'm actually looking for here? Well, what we really want is what's the probability that I picked the bias coin given that I flipped heads. That's given in the problem here. After I picked the coin, I flipped it and then looked at it and saw that it was a head. So that's really what I'm looking for here. So one way to conceive of this problem then is just really to use that definition of conditional probability. The way to think of that is what's the probability that I picked the bias coins and flipped heads divided by the probability that I flipped heads. And again, this formula just comes from this basic formula of P, A, and B equals the probability of A times the probability of B given A. In this case, I've just solved for this part of it, and I have a simple ratio here. So let's go ahead and finish this off. The probability that I picked the bias coin and flipped heads, well, what is that? We can get this right off our diagram here. Probability I picked the bias coin and flipped heads is that guy right there, 0.5. So 0.5 will be our numerator. And then the next thing is what's the probability that we flipped heads? Well, we have to look at all of our tree outcomes here. Let's see. Biased, flipped a head, so that one would be included. That's a tail, don't include it. That's a head, include it. That's a tail, don't include it. So if I add those two up to get 0.75, that's the probability that I actually flipped a head. I don't care whether I picked the fair coin or the biased coin for this purpose. I just want to know what's the probability that I flipped a head. Well, so here I'm going to put that 0.75 in the denominator. And that's everything we need here. 2/3 is in fact the answer. Okay, for this one I want to show you a different way to do this problem that some people find more intuitive. Instead of doing this probability thing, I want to just draw a tree assuming that I did this experiment 100 times. So let's assume we just repeated it 100 different times, and let's look at what should happen. If I start off with 100 coin flips, we think 50 of them should go to the biased coin. I'm going to write this here actually. 50 would go to the biased coin. Sorry about that. B. Okay, and then let's figure out what happens with my 50-50 split here once I do it. Well, on the biased coin, all 50 of them are going to be heads, and 0 are going to be tails. And for this fair coin, 25 of them will be heads, and 25 of them will be tails. So now if I asked you the question, what's the probability that I picked the bias coin given that I flipped heads? Well, one way to think about that then is just to say, well, how many heads showed up out of my 100? Well, there were 75 heads. That's my total sample space. And then how many of those heads came from the biased coin? Well, I just have to look back on the tree diagram here and I say, oh, 50 of those look like they came from the biased coin path. 50 over 75 also equals 2/3. Some people see, like, this feels it's easier for you to think of the number of coins being flipped and just kind of counting versus this more abstract notion of probability along the tree. Either way works. Just thought I would show this, and I didn't have a chance to do it in class. For part B here, I'm just going to go ahead and actually use this new method just for fun. Here we're going to assume the bias coin is weighted such that it comes up heads 80% of the time. So let's just use this new approach. We're going to assume we flip 100 coins. 50 of them are going to be on the bias path. 50 will be on the fair path because I have a 50-50 chance of picking either coin. Now when I pick the bias coin, 80% of the time it's going to come up heads. So of these 50, 40 of them are going to be heads. 10 of them will be tails. Of these 50, again, this is the fair coin, so 25 of them will end up being heads. 25 will end up being tails. And now again, we know we tipped the coin, we flipped it, and it was a head. So we're going to concern ourselves with just these two outcomes. So we know that our denominator is going to be the sum of those, which is 65. And now we want to know what percent, or which of those 65, which ones came from the biased coin. Well, just look back down the tree. Well, 40 of them came from the biased branch, 40 65ths, or 8/13ths, or that simplifies, I think, to about 0.165. So that would be the answer to this problem.